We hear so much about breakthroughs, right? Like amazing results from all these scientific studies, stuff that actually has the potential to change our lives. But I don't know if you've ever thought about this, but like, how do we even know those results are reliable in the first place? Turns out a huge part of that comes down to something that seems kind of basic: how researchers manage all their equipment and the materials they use for their experiments.
Yeah, you're absolutely right. I mean, think about it. The whole foundation of reliable scientific research, like everything from developing new medicines to making sure that everyday products are actually safe, it's all built on paying really, really close attention to detail every step of the way. And that's exactly where this idea of good laboratory practice, or GLP, comes in.
So for this deep dive, we're going way deeper than just reading headlines. We're going right down to the nuts and bolts of GLP. We're going to zero in on how what are called test systems, basically, the tools and the environments used in research, and then the actual test and reference items, too. How are those managed and kept under control? We've got a ton of information to work with here from the Code of Federal Regulations, like we've got bits and pieces of parts 110, 111, and some other GMP-related sections, and then also some really insightful discussions with regulatory experts that we found on YouTube.
Now, you might be thinking, hold on, why should I care about this? I'm not working in a research lab. Why should I be worried about how they manage beakers and machines and stuff? But here's the thing. GLP controls are like the silent guardians of reliable science. I mean, think about it. If you're trying to understand the latest health news, or maybe you work in an industry that's, affected by these regulations, or even if you're just curious about like how rigorous scientific discoveries actually are, understanding these GLP principles, it gives you real insight into why we consider certain research trustworthy and reproducible. It's like the bedrock of scientific confidence.
Absolutely. Our mission today is to really pull out the most important parts of GLP, specifically when it comes to these test systems and materials. We want to show you how these little details that you might not even think about, like how a microscope is maintained or even just how a chemical sample is labeled, they're actually fundamental to the integrity of the entire scientific process. So let's start at the very beginning. When we talk about test systems in this whole context of GLP, what are we actually talking about?
So the sources we've looked at, they don't really give us one perfect definition of test systems under GLP, but I think a good way to think about it is it includes all of the equipment and also the environmental conditions that are needed to actually do a scientific study. So we're talking everything from those really fancy analytical instruments to the rooms where they store things at specific temperatures. Like, it's basically all the physical tools and spaces that are involved in the research.
So it's like the where and the how of the research itself, right? And I guess the main point here is that these systems, they just absolutely have to be suitable for whatever job they're meant to do, right?
Exactly. The equipment needs to be able to do its job accurately and consistently, and the environment, that needs to be controlled so that nothing messes with the results. And this connects directly back to the general principles of good manufacturing practice, or GMP. At its core, GMP is all about ensuring quality and preventing things from getting contaminated during manufacturing. It's kind of like GLP takes those same really strict quality principles and applies them to the research phase.
That makes sense. Even in 21 CFR Part 110, which is all about food manufacturing, you can see that there's a huge emphasis on keeping facilities and equipment sanitary, specifically to prevent food contamination. So it's a similar idea, right? In research, you got to make sure nothing unwanted gets into your experiment and messes things up.
Exactly. And 21 CFR 110.35, just to give you an example, it specifically says how important it is to properly maintain and repair buildings, fixtures, and equipment. So if a piece of equipment breaks down, or if there's something wrong with the lab environment, say the air quality's bad, like it says in 110.20b6, that could totally mess up how reliable the study's findings are.
Okay, so we know that the research tools and environments need to be right for the task, and they have to be kept in good shape. But how do researchers actually make sure that the equipment they're using is working the way it's supposed to? That's where equipment qualification and calibration come in, right?
Right. Those are key for making sure you can trust your test systems. Based on what we learned from the EAS Consulting Group video, equipment qualification, that's how you build up confidence in your equipment. And it uses a step-by-step approach. Usually it has 4 phases: design qualification, which is often called DQ, then installation qualification, or IQ, then operational qualification, that's OQ, and lastly, performance qualification, or PQ.
Okay, so let's break that down a bit. What does each of those stages mean in practice?
Sure. So design qualification, that's basically confirming that the design of the equipment is actually appropriate for what it's going to be used for in the study. Installation qualification, that's all about making sure that the equipment was installed correctly, according to the instructions from the manufacturer. Then you've got operational qualification, which is showing that the equipment actually runs consistently within the parameters that are set for it. And finally, you've got performance qualification, and this is the part where you prove that the equipment can reliably do what it's supposed to do under normal operating conditions. So it's like a super comprehensive check at each stage, from design to actually using it every day.
So it's a very thorough process to make sure the equipment is up to the job, right? And the EAS video, they mentioned that this qualification thing, it should be done for all the major equipment and then repeated if anything major changes, like if you move the equipment. It sounds like they're really controlling things closely.
Oh, absolutely. They even talked about how if you just move a sensitive instrument a little bit, like an HPLC system, it could affect how it's installed or how it works. It really shows how closely they have to watch everything. And it's not just a one-time thing. They have to requalify the equipment every so often, or if they do major repairs, just to make sure it's still working the way it should.
Now, besides qualification, it's also calibration. So what's the difference between the two, and why is calibration so important in this whole thing?
Well, 21 CFR 111.27 and that EAS video, they both talk about calibration. Basically, it's making sure an instrument is accurate and precise. How they do it is they compare its measurements against a standard that's known to be accurate. They have to do this before they use the equipment for the first time, and then they do it regularly, either based on what the manufacturer recommends or just how often they're using it. You can almost think of it like tuning a musical instrument, making sure it's hitting all the right notes.
So it's like qualification is making sure the instrument can play the music, and calibration is making sure it's playing in tune, right? I like that analogy. And I remember the EAS video mentioned that some smaller portable instruments like pH meters and balances, they might not need the whole qualification process, but they still have to be calibrated before every single use.
Exactly. That's because their environment or how they're set up, it can change often. So doing a quick calibration helps make sure they're accurate at that moment. And another important thing, both the regulations, like in 21 CFR 111.27, and the EAS folks, they emphasized how important it is to keep logbooks, and they use those to document all the calibration and maintenance work. It's all about keeping a really clear record of how the equipment has been performing so someone can check it later if they need to.
It seems like documentation comes up a lot in these conversations. Okay, so we've covered test systems. Now, what about the actual substances being tested? The test and reference items. What are those exactly?
The test item, that's simply the substance that they're studying. It could be a brand new drug, a new ingredient for food, any material they're checking out. And the reference item, that's a substance they already know a lot about, and they use it for comparison or as a benchmark to check quality. It could be a known chemical compound, a placebo, or an older version of the test item that they've already tested. You can think of the reference item like a ruler that you use to measure the test item against.
Okay, so the test item is what we're trying to learn about, and the reference item gives us something to compare it to. So if you don't keep track of these items really carefully, it seems like you could mess up the whole study.
Oh, absolutely. If you don't know exactly what your test and reference items are, or if something happened to them, like maybe their quality got messed up, then your whole study could be totally meaningless. This is where those GMT principles of controlling components and materials come in, like what's in 21 CFR 211.80. It's all about making sure you know exactly what you've got and making sure it's kept in the right conditions.
And that leads us right into how they handle and store these items. It's not like they're just throwing them in a drawer somewhere, are they?
Definitely not. 21 CFR 211.80A, it says they need to have written procedures for every single step of the way. So from when the stuff comes in to how they store it, how they handle it during the study, how they take samples from it, how they test it, and finally, whether they say it's okay to use or if they have to reject it because it doesn't meet the standards. Those procedures, they're like a super detailed recipe for how to manage these important materials.
Written procedures for everything. It sounds incredibly detailed. And 211.80A, it specifically mentions handling and storing these items in a way that keeps them from getting contaminated. What does that look like in a real lab setting?
Well, 21 CFR 211.80C, it actually gives some examples, like they have to store things that are in bags or boxes off the floor, and they have to make sure there's enough space between them so they can clean and inspect properly. This helps stop things like bugs from getting in or damage from moisture. And another important point is in 211.80, where it says every single container needs a unique code so they can trace that batch, what they call the lot.
They put a unique code on every batch. Wow. Why do they need to track everything so closely?
That unique code, that's how they can tell the whole history of that particular batch. They can follow it from the moment it gets to the lab all the way to when they use it or dispose of it. Like, they can see if it was quarantined when it arrived, if it was approved for the study, or if they had to reject it for not meeting the quality standards. This super detailed tracking, they also talk about it in regulations like 21 CFR 111.370D for dietary supplements. What it does is it makes sure that the correct material is always being used, and if any problems come up, they can trace it all the way back to exactly where it came from. It's like each material has its own family tree.
So it's all about being accountable and being able to retrace your steps if something goes wrong, right? Like a scientific paper trail, but for the materials themselves, which takes us right to the idea of tracking and traceability throughout the whole research process.
Exactly. It's that coding system plus keeping super detailed records. That's how they achieve complete traceability, like we saw in 21 CFR 111.370. You should be able to basically reconstruct the entire history of how a product was made and controlled. You should be able to see where every single ingredient came from, how it was handled at every step, and where it ended up. And this ties in directly with good documentation practices, which we've talked about before in other deep dives. If your documentation isn't accurate and thorough, you can't really say you've got traceability.
You're right. It's not enough to just do things the right way. You have to be able to prove you did them right. Okay, so let's say you have these test and reference items. How do you know if they're good enough to actually use in a study? I'm guessing that's where quality standards and testing come in.
You got it. 21 CFR 211.84A is really clear about that. It says that every single batch that includes the ingredients, the containers for the drugs, the closures, like all the materials, they all have to be tested and approved by the quality control people before they can be used. And this isn't just a quick glance. They have to take samples that represent the whole batch and use statistically sound methods, just like it says in 211.84. They have to be totally sure that the little bit they're testing actually reflects the quality of the entire batch.
So getting the right sample to test is crucial. You can't just test a tiny bit from a big batch and assume the rest is the same.
Nope, you have to be a lot more careful than that. And the tests themselves, the methods they use, those have to be established, validated, and documented too, to make sure they're accurate, sensitive, specific, and reproducible. That's all in 21 CFR 211.165E. Basically, they have to prove that the test measures what it's supposed to and that they can get consistent results every time they do it. And then 21 CFR 211.84F and 212.71A, they make it clear if anything doesn't meet those quality standards that were set beforehand, it's rejected, no matter what.
So there's no room for error, like even if it's almost good enough.
Not a chance. Sticking to those strict quality standards is super important. If a material doesn't meet the criteria, it's rejected, period. That's how they protect the integrity of the whole study. They do have ways to reprocess materials if they need to, but even then, the reprocessed stuff, it has to go through all the same testing and meet all the original standards before they can use it.
So it seems like documentation is key to this whole thing. We've talked about procedures and records for almost everything. Why is documentation so essential for GLP?
It's simple, really. Without documentation, without keeping good records, there's no way to prove that you did all of these crucial steps correctly. We've already talked about how important standard operating procedures are. Those are the SOPs, and they need those for pretty much everything from managing the test systems to handling the materials. This is something we've also seen in our deep dives on GMP in the past. There's a huge emphasis on SOPs. What they do is they give everyone involved a really detailed guide to follow step by step.
And the regulations even spell out exactly what information needs to be documented.
Oh, yeah. For example, 21 CFR 211.67C says they have to keep detailed records every time they clean, maintain, sanitize, or inspect equipment. And both the EAS Consulting Group video and the one on good documentation practices, they both said that these records have to be legible, they have to be dated, and the person who did the work has to initial them. And if they need to make corrections, there's a specific way to do it. A single line through the mistake, then they initial it, date it, and explain why they made the change. That way, the record stays accurate.
It's all about creating a trail, so you can always look back and see who did what and when they did it.
Exactly. Just like that OS Workshop 2022 transcript mentioned, thorough documentation. It gives you a history that you can actually verify. It holds people accountable, and it lets you go back and figure out exactly what happened in a study, if there's ever a question about it, or if someone needs to investigate something.
Before we finish up, let's quickly talk about reference standards. We talked about reference items before, but how do standards fit into the picture?
So the GLP stuff we've looked at today, it doesn't really go into a ton of cocktail about reference standards, but the basic idea behind them is really important for making sure that test items are high quality and pure. Think about it this way. To test a substance properly, you need something that's already been characterized really well, and you use that as a benchmark. Remember that Catalano book excerpt, the part about APIs, which are active pharmaceutical ingredients? It said that reference standards have really specific requirements for purity. So when you have well-defined reference standards, you can be confident about whether your test item meets the quality standards. It's a really important concept in analytical chemistry and quality control. Reference standards are like the gold standard that you measure your test items against.
So to wrap up this deep dive, what we've learned is that managing and controlling test systems, and then the test and reference items too, it's not just about checking boxes and doing paperwork. All of these things like meticulously qualifying and calibrating equipment, carefully handling and tracking materials, testing everything rigorously against standards, and then documenting every single step, all of those things together, that's what makes for reliable scientific research under GLP. It's about making sure the whole process has integrity from beginning to end.
Absolutely. And for you, the listener, understanding these core principles, it helps you appreciate how trustworthy the scientific data is that impacts our lives. I mean, think about the safety of the medicines we take, the quality of the products we use every day. It all comes back to this. This is why we can be confident in certain scientific findings.
It really makes you think about all the work that goes on behind the scenes, stuff you might not even realize is happening, just to make sure that we can trust the results of scientific research. So here's something to think about. These ideas of control and traceability that we've been talking about, they're used in science with GLP. But are there other areas of your life, maybe in things you're interested in, where accuracy and reliability are really important too? And in those areas, are there details that we might not usually think about that actually make those complex systems more trustworthy?
That's a really interesting question. And if you want to dive deeper into all of this, we encourage you to check out the actual regulations like 21 CFR Parts 58, 111, and 211. Or you could look into industry guidelines like the ICH guidelines that we talked about. And of course, you can always reach out to us if you have more questions about all the little details of the laboratory practice.